new section is entitled Binomial Random Variables. An experiment that has two outcomes, success or failure, left or right, true or false, head or tail, A or B. Two outcomes. Even if this experiment is repeated many times, toss a coin 10 times. Each time, you either get head or tail. Multiple choice test with 12 questions. Answer 12 questions. That's 12 experiments. The same experiment, but each time you perform it, it's one of two outcomes, true or false. This is a binomial problem, or binomial experiment. If there's two outcomes, regardless of how many times you perform this experiment, it is a binomial problem. Okay, now I want to be very clear. It has to be the same experiment. It can't toss a coin 3 times which has two outcomes, and then answer a multiple choice test that has two answers. Now you could if the probabilities were the same, but let's not go there. There's no reason to assume that when you answer a true-false question, so it's 50-50. That's only if you're guessing. Okay. Now this is a random variable because x can only take on two numbers. Say 0 for success and 1 for failure. Actually, what do I think that it would be better if we reverse those numbers? Doesn't really matter, but 1 for success, 0 for failure. Where the probability that x equals 1, that is the probability you have success, the probability that you answer the question correctly, the probability that you were supposed to turn right and not left. Let's assume right is success and left is failure. Well, the probability that x is 0 is going to be 1 minus p. You have an 80% chance of being right, then 1 minus 80% is 20%. That is, it makes sense that this is a random variable because when you add them, the probability that x is 1 plus the probability that x is 0, you do get 1. Because if you have 1 and you take away p, but then you quickly add the p back, you're back at 1. If you have $1, say in coins, and you take away some, you don't even know how much you took away. You went over to the pile of 100 pennies, the $1 in pennies, and you grabbed some. You just pick some up, and then you put it back. Regardless of how many you originally took away, if you put back those same amount, you get 1. So here's a random variable, because when I add p of all the x's together, p of x equals 1, p of x equals 0, we get 1. So note that the probabilities have to be in this form. You can't have this equaling 80% and this equaling 30%, because that doesn't add up to 1. That would be a problem. That couldn't be. Now, let's work on a problem, and this way we could motivate how to do binomial, this random variable problems. Suppose I ask you the following. First, let's set the groundwork. The probability of getting our head is 2/3. It's a biased coin. And the probability of getting our tail will be 1/3. So you toss the coin, either you get a head or a tail. Now suppose you toss the coin 5 times. You want to know the probability you get a head or head or head. That is, the first three are heads, and then the last two are tails. What's the probability that you get this? The answer is going to be, since the tosses are independent, the result of the first toss is not going to affect the result of the second toss. That is, we can do the probabilities one at a time. The probability of the first is a head is 2/3. The second is a head is 2/3. The third is a head 2/3. And then the last two being tails will be 1/3. So we got 2/3 cubed times 1/3 squared. That's the exact value. Make that look like this 3. It's the exact value for this experiment. If you want to know, 2 cubed is 8, 1 squared is 1, so you have 8 on the bottom. And 3 cubed times 3 squared is 3 to the 5th, which I guess is what, 243? So you get 8 over 243. This is equal to 8 out of 243. Now, suppose we just do it in different order. You get a tail, and then a head, and then another head, and a tail, and a head. We still got 3 heads out of 5. The first one is a tail, so it's 1/3 times. The next one is a head, that's with probability 2/3. The next one is another head, then our tail, which is 1/3, times another head, which is 2/3. Now in multiplication, and that's what we have in front of us, multiplication, whether it's fractions or not, the order you multiply is always up to you. Well, I want to multiply the 2/3 first, and there's 3 of them. That's 2/3 cubed. And then I multiply it by the 2 1/3s. 1/3 squared. But this is exactly what we did on the problem right above. We're still getting 8 over 243. Even if I did the probability of tail, tail, head, 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 I'm still going to get 8 over 243. So if I ask you, what is the probability, if x is the random variable that counts the number of heads, what is the probability that x is 3, that the number of heads is 3? Well, what you're going to do is add up 8 over 243 a number of times. Now, of course, the question is, how many times? Now, it doesn't matter how I write the 5 outcomes, so long as there are 3 heads and 2 tails, I'm going to get the same answer. In fact, let's call this 2/3 cubed times 1/3 squared. We're going to always get this. The probability that x is 3 will have the 2/3 cubed times the 1/3 squared. It will have that. But how many times am I going to add this up? Now remember, if you're going to add up 8 over 243, or if you prefer, 2/3 cubed times 1/3 squared, if you're going to keep adding these up time and time again, you're going to add them up. 2/3 cubed, 1/3 squared. If you're going to add these up n times, 7 times, well, you're just going to get 2/3 cubed times 1/3 times n, or 7, however many times you're adding them up. Well, how many times are you going to add them up? And the question is, how many ways can you rearrange those 5 letters? How many ways can you rearrange those 5 letters? Well, from the 5 positions, you want to choose 3 of them to be heads. You might want to say, well, it's 5 factorial, but there are 3 heads and there are 2 tails, or 3 H's and 2 T's. But this is exactly what 5 choose 3 is. So this is the answer. Find out how to do any old order. You want 3 heads and 2 tails? Find out this one. Find out this one. And here it is, a nice clean form. That will be part of the answer. Look on the bottom. That will be part of the answer. Just multiply it by how many times you're going to add it up. Okay, so hopefully I did a good job in motivating the binomial formula. What we're going to do now is write down the formula. Suppose you do an experiment n times. N binomial experiments. The probability of success we'll call P. So the probability of failure will be 1 minus P. What is the probability that x is equal to I? And I is either 0 successes or 1 success, all the way up to n successes. Well, from the n, you want to choose I. From the n experiments, the tosses of 5 coins, you want to choose 3 successes. You want to choose 3 heads. And then we multiply by P, the probability success, P, and we want I successes. Then failure. The probability of failure is 1 minus P. Well, if you do n experiments, and I of them are success, and the rest are failure, it's going to be n minus 1. Sorry, n minus I. Because when you add these up, you get all n experiments. So it's going to be n take away I. And I guess over here I should write I can be 0 or 1 or 2 or 3, all the way up to the number n. In experiments, you can have only up to n successes. Okay. So that worked out nicely. So that is your formula. So, what if I asked you, back to our old problem, you toss a coin, toss 5 coins, where probability of heads is, we'll make it 1/3 now, so probability of tails is 2/3. Well, first we should define x. Let x equal the number of heads. Find the probability of getting at least 3 heads. Now, a lot of students taking probability, which means a lot of students walking the streets, do not know what at least means. And these are everyday expressions, and I hear students use it all the time. Oh, I got at least an 80 on that test. Well, I'm sure that when you say it, you know exactly what you mean. And maybe the average person walking the streets does know what at least means. But what amazes me is once they walk into a math class, they forget. This isn't math. Right now, this is everyday language. You got at least 3 heads. That means you got 3 heads, or 4 heads, or 5 heads, or 6 heads, or 7 heads, and so on. But of course, and that isn't wrong, I'm not backtracking on that, but of course, you're not, the chances that you get 6 heads are 0. The chances that you toss a coin and 5 times and you get 7 heads is highly unlikely. In fact, it's 0. Toss the coin 5 times, you'll never get 8 heads. You'll never get 7 heads. So in this case, at least 3 heads means 3, 4, or 5. So the probability that the random variable, the number of heads, x, is greater than or equal to 3. This is the probability that x is exactly 3 plus the probability that x is exactly 4 plus the probability that x is exactly 5. Now you have to be a little bit careful here. The probability of A or B or C is not the probability of A plus the probability of B plus the probability of C. For example, if I just had 2 unions, the probability of A union B is the probability of A plus the probability of B, but minus the probability of A intersect B. This top probability is not P of A plus P of B plus P of C. But if they're disjoint, if A and B don't intersect, if B and C don't intersect, if A and C don't intersect, then yes, it is valid. Yes, it is. And in our case down here, they are disjoint. If you got 3 heads, well, then you didn't get 4 heads. If you got 3 heads, you didn't get 5 heads. If you got 4 heads, you didn't get 5 heads. So yeah, we can just add them up. Now, what is the probability that you got exactly 3 heads? Well, there are 5 tosses, and you want to pick 3 slots to put H in. And the probability of success, probability of getting ahead, we said was 1/3. And we want 3 of them. The probability of failure, that is getting a tail, is 2/3. If you're tossing a coin and you're getting 3 heads, if you're tossing the coin 5 times and you're getting 3 heads, then you got 2 tails. Plus the probability that you get exactly 4 heads. So when the 5 slots, you want to pick 4 to put H's in and 1 to put a tail in. Well, the probability of getting a head is 1/3, and you want it 4 times. The probability of not getting a head, that is the probability of getting a tail, is 2/3. If you got 4 heads out of 5, you must have gotten 1 tail. Plus, the probability that x is equal to 5. Well, from the 5 slots, you want all 5 to be H's. Probability of H is 1/3 to the 5th times the probability of not an H. You want none. You want just H's, no tails. And there it is. That's the probability that x is at least 3. Okay. Now, what if we want to know the probability that it's at least 1? What's the probability that you toss a coin 10 times and you get at least 1? Or say 100 times. what's the probability that you toss a coin 100 times and get at least one head? The answer is it's pretty good. Now, okay, so toss a coin 100 times. The probability of heads, let's change it this time to 2/5. Okay, toss a coin 100 times, and I'm not sure why this didn't come out very well, so we'll do it again. I'm sorry. Okay. So we toss a coin 100 times. And it comes to be known that the probability of heads is, say, 2 out of 5. Find the probability of getting at least one head. Find the probability of getting at least one head. Okay. Now, the probability, and let x be the random variable that counts the number of heads. So we want at least one head. X is greater than or equal to 1. Well, x can be 1, and x can be 2, etc. All the way up to the unlikelihood that you got 100 heads in a row. But that's a lot of probabilities. It's 100 probabilities. One probability, oh, that says 1. Second probability, oh, look, that says 2. All the way up to x is 100. There's 100 different probabilities to compute, and that's going to take you a while. Don't want to do that on the test. You won't even finish this problem. What you should know is that the chances that you get no heads, or the chances that you get one head, or the chances that you get 2 heads, all the way up to the chances you get 100 heads, that's going to be 1. It's going to be guaranteed. If you toss a coin 100 times, you will either get 0 heads, or 1 head, or 2 heads, all the way up to 100 heads. Guaranteed. Okay, well, we want to know what this is. If you look at the line above, they look the same. We want to know what this is. Well, if you knew what that was, for argument's sake, for a moment, say it's 0.2. Well, 0.2 plus what's in the box must be 1. It's 0.8. That is, what's in the box, so it's not 0.2, at least I don't think it is. The probability of 1 plus the probability that x is 2, all the way up to the probability that x is 100. Well, on both sides of the equations, maybe I should have left more room. I didn't plan on doing this. But on both sides of the equation, let's take away the probability that x is 1. I meant to say 0. On the left-hand side, it canceled out, and what's underneath survived. And on the right-hand side, we have 1 minus the probability x is 0. This is called using the complement. I'm just going to find out one probability. Probability that x is 0. And then I'll take that away from 1. Okay, what is the probability that I get 0 heads? Well, from 100 tosses, I want to choose 0 of them. And the probability of success, the probability of heads, is 2/5, but I want none of them. Oops, I want none, 0. Times the probability of tails. Well, if 2 out of 5 times you get heads, 3 out of 5 you get tails. And this is, we want 100 of them. If you think about it, this is 1, and anything to the 0 is 1. 1 times 1 is 1, times 3/5 to the 100 is just 3/5 to the 100. So the answer is going to be 1 minus whatever 3/5 to the 100 is. Okay? So using the complement really made life easier. Instead of calculating 100 of these, I mean, look at, it wasn't that long, but it took a little time. Look how long it took to do that one, maybe a minute. So you're going to have to spend 100 minutes to do all 100, then you have to add them together. Okay, so here is a nice representative for the final answer. So the probability of getting at least one hit. So it's really good to use complements if you're being asked to calculate a lot of probabilities. Okay, if you're being asked to calculate a lot of probabilities, use complements and maybe you'll have to calculate a little. Now, if I ask you the probability in this last problem that x is 50, well then, at least 50, then you're going to have to calculate x is 50, x is 51, x is 52, x all the way up to x is 100. Trust me on this, that's 51 probabilities. If you did the complement 0 through 49, that's going to be 50 probabilities. So in that case, using complements really didn't help much. Okay. Let's try this problem. You sell light bulbs. Suppose that the probability that let's use LB, that a light bulb is defective is equal to 0.01. And the light bulbs are independent of one another. That is, just because the first 3 that you try are defective will not affect the next one. They're independent. Probability that any given light bulb is defective is 1 in 100, 0.01. Okay, now you sell these light bulbs. You sell them in packages of 5. And you offer a guarantee. You offer a money-back guarantee. You guarantee that at most one will be defective. If more than one is defective, you give your money back. You offer a money back guarantee that at most one will be defective. If one is defective, don't come bother us. We're not going to give you your money back. But if more than one is defective, you get your money back. At most one means 0 or 1 will be defective. I got a most in 80 or not test. That is, in your mind, you got 80 or below. You didn't get more than 80. Okay, so you purchase, one of your customers purchases a package of 5 light bulbs. What is the probability that they get the money back? Probability, you have to give the money back. Now, if you own this company, you should really do this. For a moment, let's assume everybody who's entitled to their money back asks for it. So now you need to decide, you need to take this into account when you decide how much to charge. In other words, maybe you charge $5 for the light bulbs and you're going to make $1 million after the year. But the problem is if you have to give back $1 million, then you broke even. So you really need to take this into account. Okay, what's the probability you have to give your money back? Well, let x equal to the number of defective light bulbs in the package of 5. You have to give your money back means that the number of defective is bigger than 1. That is, the probability that 2 are defective plus the probability that 3 are defective plus the probability 4 are defective plus the probability that all 5 are defective. Now you may say, wow, that's 4 probabilities. Maybe I should use complements. Well, either 0 are defective, or 1 will be defective, or 2 are defective, and these are all disjoint. If 1 is defective, 2 are not defective. If exactly 1 is defective, then exactly 2 can't be defective. Likewise, if exactly 1 is defective, exactly 0 can't be defective. X can have 3 defective, or you can have 4 defectives, or you can have 5 being defective. And this all adds up to 1. Now, we're being asked to find these. We're being asked to find those. Yeah, I guess I'd rather find 2 probabilities than 4. So what I'm going to do is I'm going to say this is, bring this over to the other side. It's 1 minus the probability that exactly 0 are defective or 1 is defective. So it's 1 minus, and let me erase what's on the bottom because I can use the space. And we'll calculate these 2 probabilities. And even if your teacher wants you to get the exact number, I'd rather compute those 2 probabilities and take it away from 1 than compute 4 probabilities, which you don't have to take away from 1. Okay, the probability that exactly 0 are defective. Well, there are 5 light bulbs, and you want to choose 0 for success, not defective. And the probability of being defective is 0.01, and you want none of them defective. If 1 out of 100 is defective, then 99 out of 100 are not. 0.99. 1 penny plus 99 pennies add up to 1. Okay, and you want all 5 not to be defective, plus the probability that x is 1. 5 choose 1, which is 5. Probability of being defective, you want 1 of them. Probability of not being defective is 0.99. If you have 5 light bulbs and exactly 1 is defective, exactly 4 of them are perfectly good. And there's your answer. This turns out to be 1. This turns out to be 1. So when you multiply 1 times 1 times 0.99 to the 5th, you get 0.99 to the 5th. Okay, you could compute this if you like. At least 1 means greater than 1. And in this case, greater than 1 doesn't mean 1, 2, 3, 4 forever. It just means up to 5. It doesn't even include 1.5. The probability that 1.5 light bulbs are defective is 0. The probability that exactly 6 light bulbs are defective is 0. Okay, the next problem, it's a good problem, it comes up in probability, is the following game fair. Now, what does it mean for a game to be fair? It means that in the long run, you break out even. Like, for example, in a deck of cards, 26 cards are red, 26 cards are black. If you pick a card at random, and if it's red, you win $1. If it's black, you lose $1. You play this game long enough, half the cards will be red, half the cards would have been black. You break out even. That's a fair game, when the expected value is 0. So if somebody asks you, is this game fair, what they're asking is the expected value 0? Is the following game fair? I meant to put question mark, but I'm thinking dollars and cents. Is the following game fair? Is the same as, is e of x equal to 0? Is expected value 0? If it is, then you say, yes, the game is fair. Now, here's the game. Pick a number from 1 through 6. And you toss 3 dice. Toss 3 dice. And for each time your number comes up, you win some money. If your number comes up I times, I being 1, 2, or 3, that is not 0 times. If your number comes up 1, 2, or 3 times, you win $I. If your number comes up 2 times, you win $2. If it comes up 3 times, $3. 1 time, $1. If your number does not come up, that is, you toss your 3 dice, and none of them is your number. If your number does not come up, you lose $1. And the question is this a fair game? So we want to find the expected value. Remember, the expected value is x times p of x. We write down all the values x's can be and their probabilities. Well, x can be, well, it can't be 0, excuse me. X is how much you win. And how much you win? Well, you can win -$1, that means you lost. Or you can win, that means your number didn't come up at all. Or you win $1, meaning your number came up 1 time. Or you win $2. Or you win $3. Okay, that's the probabilities. That is the probabilities. Now, what is your expected value? What's the probability that x is 1? That is, what is the probability that your number did not come up? So we're playing this game, well, actually 1 time, excuse me. We're tossing 3 dice. We want exactly none of them to be your number. The probability that it is your number is 1/6. If you pick number 4 for argument's sake, you roll it for each dice. The probability it comes up is 1/6. So basically, maybe I should say, and this is equivalent to what I'm about to say. Maybe it's better to say we toss 1 die 3 times. So we're doing the same experiment, but it's 3 times, which makes it binomial. This is the same as tossing 1 die 3 times. Okay, it's exactly the same. So each time you toss it, the chances that your number comes up is 1/6. And each time you toss it, the chances your number doesn't come up is 5 out of 6. Well, you don't want your number to come up anytime, which means you want to have it not come up all 3 times. That's the probability that x is 1. Let us remove this for a moment. Which, by the way, since this is 1 and this is 1, 5 cubed is that number, and 6 cubed I know to be that number. Now, what is the probability that x is exactly 1? Probability that your number comes up 1 time. So from this 3 outcomes, you want to have 1 success, probability of success, probability of failure. You want 1 success, which means you want 2 failures. Well, this I can see will be 75 over 216. The probability that x is equal to the number 2. Well, from the 3 choices, from the 3 tosses, you want 2 successes. The probability of success is 1/6. You want 2 of them. The probability of failure, well, if you toss the coin 3 times, then you got what you wanted 2 times, then 1 time you didn't get what you wanted. And this is 3, this is going to be 15 divided by 216. Let me erase this right here. And let us compute the last probability, that you have 3 successes. You pick 4, and you got 3 4s. They all came up 4s. From the 3 tosses, you want 3 successes. This happens to be 1. 3 choose 3 is 1. Probability of success is 1/6, and you want 3 of them. Times the probability of failure is 5/6, and you want no failures. That's also 1. So it's just 1/6 cubed, which is 1 over 216. So what is their expected value? What is their expected value? That's what we need to compute. It's x times p of x. Now let's go in the order we went in. It's this x times its probability, which will be negative 125 over 216. I predict that all the denominators will be 216. Negative 125, excuse me. Negative 125 over 216. Then x can be 1. We have plus 1 times 75 over 216, which is plus 75. And yeah, I'm dividing it by 216. Then x is 2. You have 2 times 15 over 216. 2 times 15 is 30 over 216. Then you have plus 3 times 1 over 216, which is 3 over 216. So it is correct that 216 goes on the bottom. This is what? Our 105. 105 plus 3 more is 108 minus the 125. This is negative 17 over 215. That is, if you play the game 215 times, in the long run, you would lose $17. Every time you play this game 215 times, you should expect to lose $17. And since this is not $0, it's not fair. It's not a fair game. It's a fair game if the expected value is 0. So it's not a fair game. Just because you expect to win, that doesn't make it a fair game. I was once at a church bazaar, and I was young, and I noticed that in the game they had one of the probabilities wrong. Actually, my friend noticed that. It was in our favor. So we stood there all night and we played that same number, and we actually won. And we came back the next night to make another killing, and I take it they wondered why we did so well that night, and they changed the probability so it was in their favor. Let's do another one. Suppose a circuit has 5 resistors, or 5 components. A circuit has 5 resistors. And it will work if other components go bad, it'll still work. If non-resistor components go bad, it'll work. The only time it won't work if some of the resistors don't work. The state of the resistors, the state being good or bad, defective, non-defective, that is working, is independent. If the first one goes bad, it doesn't affect the chances on the second one going bad. Let's work with that premise. The state of the resistors are independent of each other. And the state being it works or it doesn't work. And suppose the probability that a resistor is bad is 0.2, 20%. 20% of the resistors are bad. Okay, 1 in 5. Probability that the resistor is bad is 0.2. The circuit will work. The circuit will work if at least three resistors are good. So if some of the resistors are bad, it'll still work. You just have to have at least 3 working. Find the probability that it will work. Find the probability the circuit will work. The light bulb will light. The circuit will work. So that means, so let x equal the number of working resistors. I meant to put it in this line right here. But if you're really going to talk about the probability that x is greater than or equal to 3, you should state what x equals. Oh, x is the number of resistors. He wants to know, or she wants to know, the probability that the number of resistors that are working are 3 or more. At least 3. Well, this means exactly 3 or exactly 4 or exactly 5. Now you might think, what about complements? Well, in this case, I don't think it would pay off, because either 0 or bad or good, or exactly 1 is good, or exactly 2 is good, or exactly 3 is good, or exactly 4 of the resistors are good, or exactly 5 are good. And this adds up to 1. And we want to know what this is, which involves us calculating 3 probabilities. Well, if we looked at the complement, it would be 1 minus this. But this is 3 probabilities. And then you have to take it away from 1. So no, I would not use complements here. It might be worth a moment or two to think about it. But in the end, no. Now, don't spend the length of time to decide if you should use complements if it takes the same length of time to calculate 3 probabilities. In other words, if it takes you 2 minutes to do these 3 probabilities, and it's going to take you 3 or more minutes to decide, should I use conditional probability, complements, then don't do that. Because if you can do this in 2 minutes, but instead you spend 2 minutes to decide to do it, whether or not you should use complements, well then you spent 2 minutes and you didn't do you didn't calculate any probabilities. Just because you decided after 2 minutes, let's suppose you decided to use complements. Well, it still took longer because now you have to do the complements, calculate the complements. Whereas you could have found these 3 probabilities. At least that's the premise. Okay, the probability that x is exactly 3. There are 5 resistors, and we want to choose 3 of them to be good. The probability that they're good, I know the answer, I just want to I want to show you where I get it from. The probability they're bad is 0.8, so the probability of being good is the probability of bad is 0.2, so the probability of good is 0.8. We want 3 good, probability of bad. We want 2 bad. 3 plus 2 add up to the 5. Or we want 4 to be good. From the 5 resistors, we want to pick 4 to be good. 0.8 are the good ones. We want 4 of them. 0.2 are the bad ones. If 4 are good, 1 must be bad. 4 plus 1 should add up to the 5. Plus the probability that x equals 5. All 5 are good. 5 choose 5. Probability of good is 0.8. We want 5 to be good. Well, if we want all 5 to be good, then I guess we want 0 to be bad. And there it is. There it is. There is your answer. If you need to, use some calculator or whatever you use to figure these out further. The arithmetic I leave you with. You should know how to do arithmetic. And this actually completes the section on binomial random variables, calculating binomial problems. Work on some, they're fun.